Hello, it's Bill again, and welcome to another segment of Max's Come Discover Gravity series. I hope you had a chance to watch the first in the series, Come Discover Gravity with Max and me. It would help you a lot to understand this particular episode, where we're going to be talking about the relationship between E Landauer and E degree of freedom and the curvature in dark matter. So why the energy in a constrained degree of freedom is radius related? We had talked before in the previous video how E Landauer equals Landauer limit at Hawking temperature, and we found that that was the gravity emitted per Planck area according to general relativity. So we have two different sized black holes here. We have a 1 kilometer black hole and a 100 kilometer black hole. Notice that E Landauer for the 1 kilometer black hole is 1.74 times 10 to the negative 30 joules. Now the 100 kilometer black hole is 100 times the size. It has an E Landauer of 1.74 times 10 to the negative 30 joules. 2 orders difference in magnitude and scale. 2 orders difference in energy level. As radius goes up, energy level goes down. Notice that in spite of the larger black hole having more total energy, the amount of energy per Planck area goes down as a black hole's radius goes up. This is a well-known feature of black holes. Now we'll compare the gravity per emission for an Earth-sized black hole and for Earth. Notice that the black hole and Earth emit gravity at the same energy level per emission. E Landauer for both of them is 2.73 times 10 to the negative 34 joules. The difference is a black hole with a 6,370 kilometer radius is 2,000 solar masses. Earth at 6,370 kilometer radius is 10 to the negative 6 solar masses, yet they produce the same energy of level of gravity energy per emission. How can this be? So we're going to look at a piece of black hole, a wedge, and we're also going to look at a wedge from Earth. All energy levels are on the black hole's 2D surface at a distance of 1 kilometer. Everything is the same distance from the radius. This means all of the energy levels will be the same value, as there is nowhere else for other energy levels to populate. The 1 kilometer black hole will have 100 times the energy in E Landauer than a 100 kilometer black hole due to the circumference being 100 times longer. A black hole event horizon is a very dense surface and emits at very high emission rate, giving us large gravity. Earth is much less dense and emits gravity less often, giving us relatively low gravity. Now here at the wedge of Earth, Earth is a three-dimensional object, so you can see it's going to have a variety of radii. And at the surface, we have 10 to the negative 34 joules, as we had discussed on the previous slide. But let's look at the core. At the core, the gravity climbs to 1.96 times 10 to the negative 26 joules. That's 8 orders of magnitude higher than the surface. Notice at 1 kilometer from the core, we're at 10 to the negative 30 joules of energy, the same as a 1 kilometer black hole. 1,000 kilometers from the core, we're at 10 to the negative 33 joules. So 8.87 millimeters from the center of the Earth has 10,000 times higher energy than a 1 kilometer black hole per emission. In a column in Earth, the higher energy levels populate the core, and moving up towards the surface, the energy levels gradually become lower in value as the circumference sets the energy level for that radii. The gravitational energy emitted scales up as radii goes down. Now we're going to compare E degree of freedom of a 1 kilometer black hole. So we're going to look at a different way to obtain that value of E Landauer, or try to get as close as possible. Most people think that Hawking photons only come from black holes. However, Hawking photons happen every time gravity is emitted. And here's the equation for E degree of freedom, the energy contained in a constrained quantum mechanical degree of freedom that does not have any gravitational terms. And we will see that we recover the value for the Hawking photon with remarkable accuracy. And if you remember from our last video, that the Hawking photon is at the precisely same energy level as gravitational energy emission. So here is the equation. E degree of freedom equals E gamma times radius over 137 times natural log pi squared over natural log 3. So E gamma radius is the energy in joules of a photon with a wavelength equal to the object's radius. 137 is the fine structure constant denominator, stripping out charge interactions. We wanted to find out just the raw energy. We aren't interested in photonic charge. We're interested only in raw information energy. That's why we use that 137. We use the natural log of pi represents the holographic ring encoding. Notice that pi is a ring, and it actually represents ring emission. Now we have also natural log of pi over natural log of 3. So this is the scaling factor. Above you saw the factor was emitted by a ring, but this particular factor scales. So we will see this show up there. And it represents a triangular folding correction reflecting how information compresses across energy levels as curvature scales for holographic information. So this also means that we go from the curvature of the cosmic horizon at 13.8 billion light years, and then that is compressed and folded down to the object of local radius. And that's how we derive the energy levels. Now we're going to compare E Landauer to E degree of freedom for any object with 1 kilometer radius. Now we know it doesn't have to be only a black hole. We found this with no gravity terms, just the cost of that occupied space. So we have the photon here energy, 1.9878 times 10 to the negative 28 joules divided by the fine structure constant times natural log pi squared over natural log 3 equals 1.73 times 10 to the negative 30 joules. E Landauer, 1.74 times 10 to the negative 3 joules. And remember, we can take E degree of freedom and divide by Boltzmann's constant and recover the Hawking temperature for that black hole. The two methods are nearly equivalent. This means we can recover Hawking photon energy for a given radius of any system. As you can see, our method of determining the energy in a constrained degree of freedom using no gravity term at all matches very closely to the energy level determined by E Landauer, which relied on the gravitation of a black hole to calculate what amounts to curvature-based energy levels. This shows us Hawking photons are not only from black holes, but are produced anytime local gravity is produced. Nature prefers to send information in a straight line as it is much less costly. The cosmic horizon uses the triangle fold compression to turn very low cosmic horizon gravitational energy into the much higher local gravitation energy based on the scale of curvature difference. Now we're going to discuss how dark matter can come about. You're probably seeing where we're going with this. So here we have E degree of freedom for a 10 to the negative 3 meter object, a dust grain in the galactic fringe, no larger system radii to populate higher energy levels, 1.73 times 10 to the negative 24 joules. But if we take that same dust grain and put it on the surface of the Earth, it only emits 2.73 times 10 to the negative 34 joules. So you see 10 orders of magnitude difference. However, if you were to take that same dust grain and put it at the center of the Earth, then you would get right back up to that much higher level because the radius at the center of the Earth is much lower, and that object would have 10 to the negative 3 meter radius, 1 millimeter. So that's why that energy level would be so much higher. The dust mote at the far fringes of the galaxy must fill up the higher energy states at the core of the object first. Objects that have to resort to local curvature and aren't part of a larger, more energetic system will emit gravity at an energy level inversely proportional to the frequency of that local system circumference. The energy level is inversely proportional to the energy of a photon of the same radius. Higher energy levels are filled at smaller radii first, and lower energies filled at larger radii last. This same dust mote on the surface of Earth would emit gravity at 2.3 times 10 to the negative 34 joules. That 1 millimeter object emits gravity at a rate 10 billion times higher at the fringe of a galaxy. Dark matter gravitates more strongly because there is not a larger radius system available to fill the higher energy states at smaller radii first. You may have noticed something, that E degree of freedom operates somewhat like an atom's electron orbitals, except electrons assume higher energy higher energy states the further they are from the nucleus. E degree of freedom is set by the effects of radius, so small radii have a higher energy state than do larger radii. The universe truly behaves like a quantum computer, whose quantum logic energy levels are set by the system's spatial circumference and the sharing of quantum information based on a radial energy density level to quantum states. That was a mouthful. Nature is able to increase the efficiency of clocking quantum states to lower energy levels by having larger diameter, low radius system in which to communicate with all elements on that circumference. There is a natural connection between energy it takes light to circumnavigate an object and the E Landauer and E degree of freedom levels of a particle's spin energy, and also the energy level of gravity and Hawking photon emissions for a given object. Objects such as black holes are 2D objects and so have their E Landauer and E degree of freedom all exist at the same radius and therefore all at the same energy level. Objects such as planets and stars have a 3D volume in which to have the E degree of freedom levels populate higher energies at smaller radii first and lower energies at longer radii last. Not only does this apply to local object radii, it also applies to cosmic horizon radii. So once again, this type of folding, this triangulation folding, happens from the cosmic horizon all the way down to the local radius. Thanks so much for joining Max and me in talking about dark matter and how this looks like a very good model for dark matter. Please watch my other videos if you haven't. There's a lot of good information in there. Leave some comments, ask questions, and thank you very much. Have a great day.